And now I'd like to introduce our speaker for this presentation. Jesse Coro leads Earlab as Director of NA Operations, overseeing the company's strategic vision, product development, and operations. Founded in 1968, Earlab designs and manufactures sustainable ventilation solutions for the scientific research industry. Under Jesse's leadership, Earlab has emerged as an innovation leader in filtered fume hood technologies that enable significant energy savings for labs. Jesse has over 25 years of experience providing solutions to increase safety within the biopharma, pharmaceutical, medical device, and educational markets, with his specialty being focused on air filtration solutions for the protection of personnel, facilities, and the environment. Jesse's body of work includes USP 797 and 800 compliance strategies, developing sterile preparation and processing strategies, and environmental monitoring for aseptic processing. Jesse has also been assisting companies with their IAQ strategy and helping to implement solutions to create a healthier indoor environment inside and outside laboratories. Jesse, thanks for joining us.
As part of our learning objectives today, we will discuss the applications that best lend themselves to ductless fume hoods and how they should be specified. We will talk about the product designs, the features that ensure safety, performance, savings, and sustainability. And of course, we're going to talk about CapEx and OpEx savings and how we're able to achieve LEED certification and ZNE, and ultimately how ductless fume hoods become the cornerstone to your sustainability initiatives. As part of my introduction to Earlab, we have been providing filtered solutions for the protection of laboratory personnel for over 50 years. We are the inventors of ductless fume hood technology, and we continue to invest heavily in R&D to provide products that allow you to design labs in a more flexible and sustainable manner. So this is not new technology. We are not new to the market. This is a technology that we have been improving for the last 55 plus years now. Let's continue talking about the power of filtration in the future of lab design and how you can build a lab based on a green foundation. We know that ductless fume hoods consume a tremendous amount of savings because we're not tethered to the building's infrastructure. Therefore, we're not throwing out pollution into the atmosphere and we're not throwing out air. Air costs money. We also know that because we're not tethered, we're able to reduce our overall CapEx and keep our projects on schedule. We know we can reduce our OpEx and design a lab based solely on sustainability. We can reduce the carbon footprint and be the cornerstone and a clear path to you achieving your ZNE initiatives as well as your sustainability initiatives. We reduce the chemical pollution both inside and outside the lab. I will talk about that a little bit more in the presentation. And of course, we reduce the tethered constraints that you have when you design a lab based on more HVAC, more complexity. And we can do this all while improving safety. Again, I will touch on that further down in the presentation. So why is the time now? Why is it needed now? Well, it's been needed for a very long time. We know Architecture 2030 calls for the reduction incrementally of carbon emissions to zero in new buildings by 2030. Well, we know in 2021, there was studies done that said if we wait till 2030, it's too long. We need to make sure we don't heat our world up to 1.5 degrees Celsius more. It's going to be too late. We see it happening today. So we need to start designing labs today and renovating labs today with zero carbon goals in mind. We know that cities and states and legislations are trying to propose carbon taxes if we don't become ZNE. So the time is now. We know laboratories, again, consume the most amount of energy. They are 25% of the usable square footage in most facilities, yet they consume 66% of the organization's energy budget. They are a problem. So we cannot continue to design based on traditionalism because that's what we know. Had we stayed on the traditional mindset as a society, we would not advance from the horse and buggy to the vehicles we have today. If the Wright brothers weren't innovative in their approach in being adamant and finding a way to flight, we would not have the airplanes we have today in the form of transportation we have today. We have to step aside from the mindset of traditionalism and embrace change in order to meet these initiatives. And we're doing that today in many different regards throughout our forms of transportation, with our way of living, with solar panels, but labs still remain a constant problem. Again, the good transition into the problem. We know ducted hoods consume a lot of energy. They starve the air handling units. They reduce the air needed for proper dilution. We know the cost of airing has increased by 54% since 2006. This puts a hole in our pockets. That's not the biggest problem. The biggest problems are, as far as I'm concerned, the pollution that we throw into atmosphere and the CO2 that's generated from these hoods. We'll talk about reentrainment in a moment when we talk about EPA regulations, but that occurs from adjacent buildings in the very same building you're throwing pollution out of. We know the environmental impact of pollution. In fact, we know we can't be just dumping pollution into the rivers anymore, right? We've seen rivers catch on fire because of pollution, but why is it okay to just assume we can do that in the air that we breathe every day and assume dilution is the solution to pollution? We can't. We have to think differently. The carbon impact of one ducted fume hood consumes about 22,000 pounds of CO2. Even if we cut that in half, that's 11,000 pounds of CO2 generated every single year from one ducted fume hood. Consider that when we think we have over 750,000 ducted fume hoods in this country alone. We must start thinking differently and not be fearful of change. And I will make sure that everyone is rested easy when we talk about the safety aspect of this technology. Now we're going to talk about two different carbon types, embodied carbon and operational carbon. Embodied carbon is that's associated with the manufacturing and the use of the products or services. And of course, operational carbon speaks for itself. It's the operating of the equipment and how much carbon, what's the carbon impact of that equipment. We're going to talk about both and how we're able to provide solutions both on the embodied side and the operational side. So let's look at some of the cost considerations. When we look at a ducted fume hood, again, I've already talked about the impact it has, but we have to understand a ducted fume hood is connected, it's tethered. That costs money. That has a tremendous carbon footprint when we talk about embodied carbon. Exhaust stacks, fans, blowers, HVAC runs, or duct work. It adds up. In addition to that, it has a significant impact on your bottom line. One 6-foot ducted fume hood is about $2,900 per square foot to install. On a 6-foot fume hood, that's $43,000 for one fume hood. Has a huge impact, and not many people think about that. They think about the hood, they purchase the hood for, I don't know, $10,000 to $15,000, and that's the cost. It's not. It has a cascade effect. But then we look at the cost of ductless fume hoods. While the hood itself is more money, we have reduced the embodied carbon footprint because we take away all the HVAC runs, the blowers, the fans, the valve control systems. So our embodied carbon is taken care of here. Total cost is about $2,100 a square foot. On a 6-foot fume hood, that's $31,000. It's a reduction of about 27%. So right off the bat, we see the savings on the first cost savings on the CapEx side. Let me take you to a real study. This is Framingham State University, and they designed their lab with 49 ductless fume hoods in 2014. The ductless fume hoods were value engineered onto this project after budgeting revealed a gap in funding from the state. And as we all know, these efforts do not return complete savings. But even with the study, it was over $6,700 per hood CapEx savings. The architects on the project immediately, because it was designed initially as a ducted project, they said, man, I wish this was designed around ductless fume hoods from the beginning. That way we could have reduced our floor-to-floor heights and saved even more. But even with this savings, again, $6,700 per hood, are a gross savings of $330,000. And we look at the impact on design. 100% ducted, you look at the complexities. Again, you have to increase the floor-to-floor height, therefore increasing costs. It's a very complex design. But then we take that out of the factor and we install ductless fume hoods and we simplify the design. Again, value engineering it, reducing the floor-to-floor ratio if it was originally designed with ductless fume hoods, and reducing the CapEx. And of course, the operational side of things, which they calculated to be about $25,000 annually in net operating cost, and which included filter changeouts and routine maintenance. After further calculations, the savings is much higher than that because the filters lasted longer than originally intended based on our studying and evaluation, which we'll touch on later in the presentation. To continue talking about the impact of traditional design, again, ducted fume hoods. This is a hood-intensive lab with 10 ducted fume hoods. Everything is increased. Your HVAC runs, your MEP equipment, your supply air, your blowers, your chillers, your cooling towers, your exhaust fan. It's more higher construction cost, higher operating cost. Take the duct out. Even if we make this a hybrid lab and only half of the hoods become ductless hoods, you reduce the lab's total exhaust air. You reduce the lab's ventilation. You increase the square footage available for your operations. With ductless, it's more. It becomes more savings, more room to operate, more flexibility. We take that 10 hood chemistry lab and we peel back the layers to really truly understand the impact the supply and the exhaust air has on a fully ducted design versus that of a hybrid approach. And we can see the impact in the next couple slides here. So you look at this 10 hood chemistry teaching lab, hood intensive lab, and you look at the supply air that's needed if you need to supply enough air to operate these 10 hoods on a ducted system. You look at a total CFM max of 7,200 and a total minimum CFM of about 1,200 supply and 1,500 exhaust. When you increase your CFM to 7,500, you increase what's necessary for air exchange rates to be typically between 4 in an unoccupied space and 6 in an occupied space. You increase that to 20 air exchange rates per hour. More air, more money, unnecessary amounts of air movement, massively increasing your total operational expenses. Now, if we take that same lab and we convert 7 of those hoods to ductless fume hoods or filtered fume hoods, and we keep 3 of those hoods being ducted, we drastically reduce your CFM intake to 1,200. That's the same 1,200 in, 1,500 out. But you reduce your occupied and your usage space down to 1,950 CFM max. It's a 5,200 CFM savings, which is a significant reduction in cost. And even if you say, well, we only use this lab 35% of the time, you're still saving over $13,000 a year. That's almost $2,000 per hood. And that far outweighs the cost of what you're going to be spending on maintenance and filter changes, which is about on average every 4 to 5 years. So you quickly can see the value engineering impact that it will have on your facility. Let's talk about the environmental impact. We look at the environmental impact of a traditional lab. Fossil fuels, you look at, the embodied carbon, everything that's moving and going, all the pollution that's thrown out into atmosphere, the CO2 emissions. You can't hide this. You know this happens in a lab today. We know from a study from Lawrence Berkeley National Labs that one single ducted fume hood consumes as much energy as 3.5 U.S. homes. Of all lab equipment, ducted fume hoods consume the most energy. I've already touched on this. At Cornell University, this is a fun fact, and I learned this from a presentation I gave at Cornell. Their labs take up about 20% of their space on campus, but they use 40% of the campus's energy. Again, it just solidifies why we're having this conversation today. When we look up the 20-year operational carbon footprint from a ducted fume hood to a ductless fume hood, it's a 94% reduction. Why? Because you're able to reduce, again, gas and electricity. We look at the embodied carbon, which is really inconsequential when you look at how much is consumed with gas and electricity. And you look at the overall gas and electricity spend for a ductless fume hood. This operational carbon obviously includes filter replacement and the continuous rotation of filters every 4 to 5 years. It's all includes that, and we still see a 94% reduction. It's significant. Now, it is important to know that our filters are made mainly, the organic media is coconut shell. So we have a very clean process from the filling of the carbon to picking the carbon, creating clean CO2 with the trees that are necessary to grow the coconut trees through incineration, and obviously through usage and incineration. And I will touch on the incineration in a moment. So the life cycle of chemicals, again, we talk about the environmental impact. We have to understand the life cycle of the chemical in the atmosphere. We know that as per the EPA regulations, they allow 100% of the TLV to be released at the exhaust stack. And they're hoping that within 450 feet, that the pollution will dilute. Again, dilution is a solution to pollution. It is not. Again, we learned our lesson with just throwing everything into the rivers and assuming, yeah, it's big enough, it will dilute all the chemicals we throw in there. Or how about we just go look at the trash islands we have in the ocean? Because, why not? The ocean is vast. We cannot continue to treat our world this way. We must do things differently. And I would like to point out that as per ANSI Z95, it requires that the hood exhaust, it needs to avoid reentry into the building or adjacent buildings at concentrations not above 20% of the allowable limit. Inside the lab for routine emissions, or if there's an emergency, 100% of the allowable concentration for emergency emissions. With ductless fume hoods, we don't allow more than 1% of the allowable emissions or TLV to be released at the filter's exhaust. So just think about that for a moment. Which system's really safe? Now, there's a time and there's a place for ducted fume hoods. We can't avoid that because of certain applications and certain handlings. But the majority, and I'm going to be bold here and say the majority of hoods today can be used with ductless filtration technology. Some may challenge me on that, but I can tell you, we do an evaluation of many, many different chemistries. We can handle a vast majority of what is handled within ducted fume hoods today can be handled in ductless fume hoods because of our technology. Let's talk about disposal because this is part of the environmental impact. Once a filter is used, the proper way of disposal is through incineration. Now, not many people realize that the incinerators that are used create clean energy through turbine generators. When the filters are incinerated, they create steam and flue gases. Again, the turbine generator collects that, converts it into 14 megawatts of energy, and then those flue gases are then scrubbed through their own filtration system, goes out the stack, and creates clean water vapor and flue gases. Very clean process. And then one of our filters, once incinerated, converts down to about 3/4 of a cup of ash. So we drastically reduce our environmental impact, both from on the embodied side and on the operational side. And in fact, these incinerators have to adhere to the EPA guidelines of 264343, which essentially means of every 10,000 molecules, anything that's released out of their stack must be reduced down to 1. They have to have a 99.99% efficiency. So let's show some real world results now. Let's get into the meat of the impact we've had on different facilities. The first case study is Bristol Community College. And I'll walk you through this because they try to achieve ZNE in a northeast climate or zone 5 with ducted fume hoods. But they realized these ducted fume hoods consumed half of the PV arrays that were installed. Lead Silver Plus design was proven even to be inadequate. So they had to figure out a different way to design this lab if they really truly wanted to meet ZNE. So they ultimately went with filtration. They still have ducted fume hoods, but they ultimately went with ductless fume hoods, 17 filtered fume hoods to be accurate. They reduced the facility's makeup air requirements from 70,000 down to 24,000 CFM. Their MEP equipment was reduced by 14%, and they achieved ZNE with zero additional cost. And their energy use intensity went down significantly. We're going to talk about that in the next few slides. And now they have more usable square footage. Again, traditional mindset was to design with ducted fume hoods, quickly realized was not going to be able to happen based on their sustainability goals and initiatives. And when you look at the design, the initial design was a high-performance building utilizing 22 ducted fume hoods. The project was put on hold because during the time of design, the president of Bristol Community College signed the 2050 Zero CO2 Challenge. So when funds became available, the president of the school said there was no way to meet the challenge if they built a high-performance design. So they re-engineered the building ZNE, which included ductless fume hoods, ultimately saving what I told you before, 70,000 CFM It was a 67% reduction in hourly air changes, significant. So it just shows you, we have to look at alternatives and step away from tradition. And when we look at the baseline building, when it was designed at 290 energy and as an energy use intensity. The high performance design reduced the load by 60 EUIs, and it allowed the design to achieve LEED Silver almost. By switching to ductless fume hoods, they had a single highest reduction in load on the building and achieved LEED Platinum status and ultimately ZNE. Additional energy savings measured and the addition of the solar PV arrays, solar hot water collectors allowed the project to be certified -13 EUI positive net energy. Again, cascade effect and a significant impact. We'll take a look at Lafayette College. Again, the goal for the facility was to be reduced the consumption by 45% below the LEED baseline. The project was designed to meet LEED Gold or better. And, furthermore, the college climate action plan was pledged to reach the carbon neutrality by 2035. Ultimately, the result was an inefficient biology building, resulting in a 40% reduction in campus CO2 emissions. So we were able to reduce that by 40%, 74% reduction in energy use intensity as compared to the 2030 baseline. And we helped them achieve LEED Platinum certification. They're an AIA CODI Top 10 2021 design, again, because of ductless fume hoods being the cornerstone. Then we look at a facility, Northeastern University, which is 77 fume hoods, 6-foot filtered fume hoods, which are actually lab Conco hoods where they integrate our filtration technology. And we see the significant savings here, which actually was able to save them 350,000 gross square foot of space. The fit out was late 22. Occupancy was actually, at the update, that was actually in 2024. We see the reductions. Ultimately, the third floor teaching labs were designed with a combination of ductless fume hoods for the students and ducted fume hoods for the chemical prep and waste collection. Again, ducted fume hoods still have their place for sure. We're not saying that they don't, but again, of all those fume hoods, 77 were ductless, 19 were ducted. So it just goes to show you the majority of these hoods could be ductless efficiently and effectively. When we look at eliminating the embodied carbon, 77 hoods had an impact of 77,000 CFM in savings. Massive savings. And we look at the boilers and the chillers, the air handling units, the massive impact it has had on the design of this lab. We're very, very proud of the design. We're very proud of the installation. We'll look at an organic chemistry teaching lab at Carleton College. Again, this was a new construction. They wanted to have a swing space, and we're actually very involved in a lot of swing spaces where they wanted to keep the chemistry lab operational during construction, and they can't do it with ducted hoods. It's near impossible to do so. So they had installed ductless fume hoods, but they realized the efficiency and the effectiveness, and ultimately the design of Carleton College included filtered fume hoods throughout the whole facility. 9 filtered fume hoods. The ducted fume hoods served as, the teacher's waste collection and hood prep area. So again, a perfect marriage of a combination of ductless and ducted fume hoods. Wellesley College, very similar to Carleton College, where they needed a swing space, but ultimately realized there's more to these ductless fume hoods than meets the eye, and the facility was designed with 39 filtered fume hoods and 40 ducted fume hoods, almost a 50-50 split there. And we had tremendous savings, a great install. So final thoughts on that end of the presentation is you capture and retain contaminants at the source is critical to really having a true sustainable lab. Reducing the ventilation and air requirements is instrumental to achieving your LEED or Z&E and your sustainability initiatives. And we know that we can lower first cost and operational cost savings. And we know for sure pollution is pollution regardless of dilution. Can't hide that fact. If only we could see the amount of pollution. The last case study I want to have, because those were my final thoughts on the first part of the presentation, but the last case study is Butler University. The scope was 30 green fume hoods, what we call green fume hoods, so ductless fume hoods, 12 capped air for rotary evaporator hoods. I'll talk about the difference between capped air and GFH hoods. It's really about the structure. We have some additional technology on top, the heart of the technology itself, but the structure, which really allows us to comply with different standards versus the capped air structure, which is a single wall, very simple structure, certainly has its place on hundreds of thousands of labs, hundreds of thousands of installation. It's an extremely well-designed product, really used as a ductless fume hood as well, but obviously equipment enclosures can be fully customized to meet the customer's needs. And then we have our whole ecosystem of filtration solutions, which Butler has in 2 filtering storage cabinets, halos over the solvent disposal station, and more based on their new lab build-out that they just completed at the end of last year. Their original design was for 26 ducted fume hoods, but again, they wanted to figure out a way to value engineer, hit their sustainability initiatives. So they looked at filtered fume hoods, and they realized quickly the first cost savings was there. We had $160,000 in CapEx savings. But then, of course, we wanted to look at the operational budget, and they realized quickly after many studies, going after the low flow hood at 744 CFM at a yearly CFM cost of $5 per CFM. They said, wow, 10-year operating cost on a ducted fume hoods would have been almost $1 million versus that of the filtered fume hoods of almost or less than $400,000 with the total operational cost, including filter changeouts of $390,000. The savings is substantial. And that was based off our original analysis of the filters only being changed out every 2 years. And they changed their filters out every 5 after many testing, sending their filters to Pace Analytical to do leach testing to see if they're used, if they have any more residency sites, and could not get these filters to fail. But they really decided after 5 years, we may be pushing it. So they replaced their filters after 5 years, and they are a continuous repeat customer. And of course, this slide shows you the impact on the design before and after, very similar to what we saw earlier on the Framingham State University project. So let's talk about safety. We have to talk about the ductless fume hoods, the standards harmonization, and apologize for my lack of English there. But we have to look at all the different standards. So a lot of questions we are asked is, what about safety standards? Do you comply? Well, we comply with ANSI Z95 2022, NFPA 45 2024, CSI Z316, and AFNOR NFX 15-11, which is a European-based standard, which these standards actually point to, because this is the hardest standard to comply to when it comes to filtration. So what do these standards mean? Well, with ANSI, you must have, when you're talking a ductless fume hood, you must have 2 layers of redundancy. Same with NFPA, same with CSA. With AFNOR, you allow for 1 or 2, but really you want to go 2 layers of redundancy when we're talking about research grade chemistry, organic chem labs, things of that nature. Only going 1 layer of carbon is high school chemistry. But ANSI, you want 2 layers, again, 2 layers with NFPA, 2 layers with CSA. The structure needs to be same as a ducted fume hood as per ANSI, NFPA, and CSA standards. We have that solution with our partnership with LabConco. That would not comply with the capped air, but it does with the LabConco structure for sure. So we comply with every one of these standards. And of course, you have to look at the allowable exhaust percentage of the TLV. ANSI allows for 25%. NFPA points to ANSI. CSA is a fraction of the OEL, but AFNOR only allows for 1% of the threshold limit value to be at the exhaust. This is the golden standard when it comes to filtration, hands down. And I'm going to give a quick 101 on the AFNOR standard. And of course, containment testing, we have to comply with ASHRAE 110. We do that on the capped air side, but also on the structural side with LabConco. So let's talk about the AFNOR standard. What does that mean, and why is this the golden child of standard for filtration? The AFNOR standard encompasses, obviously, filtration efficiency, containment efficiency, airface velocity, and we must have documentation understanding the chemicals that can be retained by the filtration technology. It's a very, very tedious testing process that must be performed to ensure the safety and performance of the filters. Filters are not and cannot, especially at the molecular level, be determined on their efficiency on time. We have to understand evaporation rates, quantities, vapor pressures, and what that filter can retain for every chemical and the families of chemicals. So again, to summarize AFNOR, you must have documentation which provides a list of chemicals. We have that. It's our chemical listing booklet, which is available as an asset. It's over 750 chemicals, which we have tested under 6 different concentrations twice. It represents thousands of chemicals. We know down to the molecular gram that you can retain of every one of these chemicals, and it's stated in this book, before we've seen release not exceeding 1% of the threshold limit value. All of this testing has been performed in a hermetically sealed chamber here with GCs on top so that we capture release at the source and without dilution. We must provide a certificate of validation based on the handlings of the customers within the enclosure and guarantee a filter life cycle. So when we perform an analysis or a risk assessment study, we determine what the overall life cycle of that filter is, and it's our guarantee. If we say that filter is going to last 24 months, 36 months, 48 months, we guarantee as long as you use those chemicals according to the assessment that you provided, there will not be release exceeding 1% of the threshold limit value during normal operating phase. And then you must have third-party validation and test data, which we do through Intertech. Here is that chemical book. It just gives you a snapshot of what it looks like. Again, the list of chemicals, the CAS number, the retention value of what we can retain of those chemicals per filter before we've seen release not exceeding 1% of the threshold limit value. And we have global threshold limit values, or OELs, here across the globe, because we are a global company. And we always take the lowest value globally of what we're able to retain. Now we must provide safety under, again, those 3 operating phases. I mentioned normal operating phase, guarantee of no more exhaust exceeding 1% of the threshold limit value. Then you have detection phase. What does detection phase mean? Well, we have sensors built into this technology within the fan module, whether it be a solvent sensor, an acid sensor, a formaldehyde sensor, or potentially a combination of all 3, in which we will detect any spikes of concentration that may come off of this primary filter. That's determined by a millivolt setting based on the prominent breakthrough chemical, and it will alert that we have breakthrough. But because we have redundancy, this is detection phase, we still guarantee that you will not see release exceeding 1% of the threshold limit value. Now, if you only went 1 layer of carbon filtration, which we don't recommend, but if you do, at detection phase, you would have 50% of the TLV at the filter's exhaust. But that's very low chemistry handlings at the high school level. 98% of our customers go with 2 layers, obviously. Then you have safety phase. We have to take this a step further. What is safety phase? Safety phase is at which point the hood itself, the technology, has been alerting you that we've had breakthrough. Now, you are alerted via smart light technology. You also have a web-based platform, embedded web-based platform, where you can get real-time data points of the performance of the product. If this is ignored, which it can't be because the light flashes and there's an audible, if this is ignored and then you have a spill within the fume hood, this is at which point we consider the hood to be in safety phase. At this point, we guarantee still the concentration at the filter's exhaust must be lower than 50% of the TLV for 1/12 of the filter life cycle. Hood should never get in safety phase. If it does, you have to take accountability for that and have to put in proper administrative controls. We have safety specialists that constantly manage our accounts to make sure the filters are changed according to lab recommendations. And if there is an alarm, we talk with the customer. There's SOPs written that they let us know that there's an alarm so we can rectify the situation. Now, I talked about all of the capabilities we have. We also must understand our limitations. Limitations are basically this short list of chemicals: noble gases, chemicals which are naturally gaseous under normal temperature and pressure conditions at very low boiling points. You're using these chemicals, we cannot retain them. You have to go with the ducted fume hood. And then those that are not recommended below. Again, you're using these chemicals, you have to go with a ducted fume hood. And that's okay. We've learned from these case studies, they can live together. But again, the majority can be designed around filtration. I do want to talk about the NFPA standard real quick because that's a question that's brought up quite a lot. And how do we comply? We are in full compliance as long as we use the structure from LabConco. The difference, again, is based on structure when we go from capped air or we go with a ductless fume hood from LabConco, which is the Echo Aero, which allows us to comply with the NFPA 45 standard. Everything else in regards to the filtration, the automatic detection breakthrough, we comply with as per AFNOR, NFX 15-11, but on the structural side, we comply with our partnership with LabConco. So we do have a solution there. The updates within NFPA 45 2024 as compared to other editions, ductless fume hoods shall be allowed to be used for specific chemicals and if defined quantities, which we do with every product we sell in any type of setting. A detailed application review, hazardous analysis and risk assessment, plus manufacturer's pre-approval. Check mark, we do that. Recirculation of air within the lab area from ductless fume hoods is absolutely permitted if we comply with these callouts, and we do. Additional requirements, operating procedures, training, and administrative controls with annual reviews. Check, we have that. Signage and labeling on each ductless fume hoods. LabConco does a phenomenal job at that with their signage right on the front of the hood structure, and you must have a minimum air gap clearly defined of 4 inches. Not a problem at all. So standards and updates for CSA Z316. They're going to incorporate ductless fume hoods, 2 layers of carbon. Filtration must be on the ductless fume hood. You must have automatic detection, must have EH&S's involvement, which they're involved with at all times as they should be. You must have user training, and ANSI Z95 2022 updates, same thing, 2 layers, continuous monitoring, detailed application review, which we have. Again, we meet in full compliance. I do want to talk about smart technology real quick. I talked about the light technology. We have smart light technology on all of our products. If the light remains steady it means that the hood's operating at peak operational performance. If it pulses, we're detecting air face velocity alarm, meaning we have less air entering the hood. If it's a storage cabinet, the door is left open. We've had a detection or a breakthrough past the primary stage of filtration, or we've had a ventilation fault failure, and we even have ambient air quality sensing with our Halo whole room air filtration systems. And then we do have our web-based embedded platform where you can get real-time data points of the product's performance. So with that quick video, there's a better way. There's a better way with filtration. I talked about that. I have been talking for a long time. There's a lot of information here, but there needs to be, because there's a lot of preconceived notions about ductless technology, where to apply it, what its capabilities are. Now you'll see in this quick video, you just saw some smoke being generated from a nickel test, and you realize, where's that smoke go? Well, we have the capabilities of also integrating HEPA filtration into all of our products. So it's really a multi filtration approach where you can go HEPA filtration and a combination of carbon with HEPA, obviously for smoke. If you're doing any type of acid digestion, or if you're just using particles, you can use these products as weighing stations as well. And what you see here is that Halo system. That's our whole air filtration system, which can be equipped with carbon or HEPA filtration, depending upon the contaminants that we're looking to scrub the facility with, providing cleaner air. So again, a holistic approach to lab safety, a more flexible, sustainable design. So in summary, again, filter fume hoods in general are the cornerstone to achieving sustainability and ZNE goals. It can be balance of ducted and filtered fume hoods. We must all do our part to help save our environment. And the good news is there's solutions. And we must look at ways to improve inefficient engineered control systems. So with that, I thank you. And I know there's a lot there, so I look forward to the questions that you have.